Hey guys, today I'm going to start a video lecture series on Chapter E. So my video lectures are meant to be an overview of the chapter. It's not meant to be all-inclusive. I'm going to try to cover some of the harder material from each of the chapters, break that down a little bit for you. So our first video from Chapter E. First thing we're going to talk about is measurements and expressing results. So as a chemist, as a scientist, we're certainly going to take lots and lots of measurements. So we want to make sure that we're doing that the correct way so that when we report our data, it is the same across the board. There's going to be two types of measurements that we talk about, or two types of numbers, I should say, that we talk about. So the first one is going to be counting numbers, and the second one is going to be a measurement. A counting number is going to be an exact number, or it's going to be a definition. So if we look at the screen here, I see that I have 1, 2, 3, 4, 5, 6, 7 pennies on the screen. I don't have 6.9. I don't have 7.1. I have exactly 7 pennies, and there's no uncertainty in that. So that would be a counting number. And like I said, a definition is also an example of a counting number. The other one you see on the screen is a measurement. So with a measurement, we're going to use an instrument to record a certain value. So whether it's weight or volume or mass or whatever, length. So the first thing that we see here is a digital scale. So this digital scale is going to be one of the instruments that we use. And on this digital scale, we see a number that spits off. So it looks like we're weighing a nickel here, and it spits off 5.01 grams. When we're talking about reporting measurements, we're going to talk about something called significant figures. So significant figures are going to tell us how accurate, precise, that instrument is. So when we're recording numbers off of a instrument, we're going to write down all of the numbers that are certain plus one estimated digit. This seems kind of silly with a digital scale, or really any digital measurement, because the scale does the estimating for you. So I might pick up that nickel, put it back down. It would read 5.02. I pick it back up, I put it back down. It reads 5.00. So the estimated digit is where uncertainty starts to creep in. All of these digits, however, are significant. So if I said, well, how many significant digits does this scale give us? It gives us 1, 2, 3 significant digits. 1, 2, 3. So 3 sig figs, or 3 significant digits. Here we see another example of a digital scale. So on this scale, we're measuring a blue blob, let's say. This blue blob, when I put it on this scale, it reads 10.5 grams. So how many significant figures are in that measurement? There's 3. And which digit is estimated? It would be that last 5. So I may pick up the blob, put it back down, and it reads 10.6. Here we see another scale measuring the exact same blue blob. So I just picked it up off of one scale, put it onto the other scale. What I see with this scale is it gives me a lot more digits. So it's 10.4977. So how many significant digits does this scale give me? 1, 2, 3, 4, 5, 6 significant digits. Where is the uncertainty for this scale? Well, the uncertainty doesn't creep in. It's all the way out here at this last 7. So if I had to pick which scale I wanted to use, I would certainly pick this scale over here on the right, as it gives me more significant digits. Uncertainty creeps in much later in the number, so it's going to give me a better value as to what that blue blob actually weighs. Okay, so what if we don't have a digital instrument? What if we have to do the measuring and the estimating ourselves? Here we see a graduated cylinder. And we want to measure how much water is in this graduated cylinder. First thing I want to talk about is when we measure water in a graduated cylinder, we see this kind of dip in the water here. That dip is called the meniscus. And anytime we want to measure how much water we have, we always go to the very bottom of this meniscus to measure how much we have. Up here on the sides is actually the water sticking to the glass. So the actual value, the actual amount of water is down here on the bottom. All right, so when I write down a measurement, I'm going to write down all of the numbers that are certain. So without a shadow of a doubt, the instrument tells me. And then the last digit I'm going to write down is estimated. So looking at this particular instrument, I see these big numbers here. So I'm going to assume this is 4 milliliters, 5 milliliters, and up here this would be 6 milliliters. Okay. So I know this water level, without a shadow of a doubt, is somewhere between 4 and 5 milliliters. So there's at least 4 milliliters of water. I know that without a shadow of a doubt. The instrument tells me that. So I'm going to go ahead and write that down. So there's at least 4. Okay. Between the 4 and the 5 are these little tick marks. And these tick marks tell me with certainty something else about the water level. So the tick marks are going to be a decimal. And if I start down here at the 4, get my pointer here again. If I start down here at the 4, this is going to be 4.1, 0.2, 0.3, 0.4, 0.5, 0.6, so on. So I know this water lies somewhere between the 0.5 and 0.6. So without a shadow of a doubt, I know that there's at least 4.5 milliliters. These tick marks tell me that there's at least 4.5. There's no more tick marks in between these two that tell me anything else about the water level. So the next digit I'm going to write down will be the estimated digit. And here's where a little bit of uncertainty creeps in. So I look at this water level and I say, you know what? It's really, really close to this 0.6. So I'm going to estimate that as 5.48 milliliters. Somebody else may write down 4.59. Somebody else may write down 4.55. So that last digit is a little bit subjective. It is an estimated digit, so it may vary from student to student. How many significant figures did this instrument give me? This instrument gave me 3 significant figures. The next thing we're going to talk about is scientific notation. So let's think about some of the measurements that we take in science. In biology, you might take some measurements that are pretty standard, so the length of a tail, the length of a snake. In physics, you may measure the distance from here to the sun, so it's a really, really big number. In chemistry, we're talking about the size of atoms, so really, really, really small number, and the number of molecules in a cup of water, so another really, really, really big number. So we use scientific notation in the sciences to help us reel in numbers, make them a little bit more user-friendly. Scientific notation is also going to help us a little bit later when we come back to the idea of sig figs. Here we have a laser. This laser is measuring in femtoseconds. So you don't need to know that, but it's measuring really, really fast speeds. So if I were the scientist that was doing work with this particular laser and I was going to report these measurements, I certainly would not want to report all of those zeros every single time I wanted to write down a number. Or if I was the scientist that was reading that work, I wouldn't want to count every single one of those zeros every time I wanted to know what that measurement was. We use scientific notation to reel it in. So here's the standard setup for scientific notation. We have our coefficient piece. So this is going to be moving the decimal till we get a number between 1 and 10. So 0.12 would not be correct. 12.0 would not be correct. We want a number between 1 and 10, so 1.2. Then after we move the decimal, we're going to multiply that by 10. And then this exponent is going to be how many places that we moved the decimal. So if I were to do this one, I moved it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 spaces. So I'm telling the viewer I moved it over 15 spaces. And because I moved it over to the right, it's a negative exponent. Being a dyslexic, left and right never really worked well for me. So the way that I actually remember the negative exponent is if it's a number that is less than 1, the exponent will be negative. And if it's a number greater than 1, the exponent will be positive. So left, right, above 1, lower than 1, whatever works for you, just find a path that works for you. So here's the words version of what I just said. So move the decimal to get a number between 1 and 10. Write the result from step 1, multiplied by 10, raised to the number of places that you moved it. The next thing we're going to talk about, and this is where scientific notation will help us. The next thing we're going to talk about are significant figure rules. So we may not always be the one that's taking the measurement. We may be the one that is reading a number from somebody else that's reported it. So we want to be able to look at a number and know exactly how many significant figures are in that number. This will also be important when we start doing math with numbers. We have to know how many sig figs are there as well. So first rule is all non-zero digits are significant. So zeros are where things get a little bit tricky. So anything that's not a zero, it's certainly going to be significant. So a number like 5,723 miles. Okay. So none of those are zeros. All of those are significant. So that has 4 sig figs. And I often abbreviate significant figures as just SF. Any interior zeros are significant. So if you find a zero smack in the middle of a number, that zero is a significant zero, and we would certainly count that. So an example of this might be 103.5 degrees Fahrenheit. So we see that zero right in the middle of the number, so that one is certainly significant. So again, this one would have 4 sig figs, the 1, the 0, the 3, the 5. Now we're getting a little bit trickier. So any zeros after a decimal, after a number, are significant. So after a decimal, after a number. An example of this would be something like 3.0 centimeters. So after a number, so I see this number 3 is in the front. After a decimal, so there's my decimal, then I bother to write a 0. So if it's after a decimal, after a number, it is significant. It's there for a reason. So this one would have 2 sig figs. Kind of the silly way that I remember this is chemists are lazy. We do not write anything out. We use abbreviations for everything. So as a lazy chemist, if I bothered to write a decimal, then I bothered to put a 0 after that decimal, I did so for a reason. The instrument gave me that information. So in this case, the 0 would be the estimated digit. So I estimate that the length of whatever fell right on that 0 line. So after a decimal, after a number, if I bothered to write it, it's there for a reason. I'm lazy. I wouldn't do it otherwise. So those are what are significant. Now we're going to talk about things that are not. Any leading zeros are not significant. They are simply placeholders. So we've seen an example of this already. I'm not going to write all the zeros again, but something that looks like this. So these zeros are the first thing that I came into contact with. There's no other number before those zeros. So that's a leading zero. They are simply placeholders, or they're holding the magnitude of this number. So the only numbers that are significant here are the 1 and the 2. So this one also has 2 sig figs. Here's where scientific notation is helpful. If I were to put this number into scientific notation, what would it look like? I would move the decimal over until I get a number between 1 and 10. So 1.2 times 10. And now I need to tell the viewer how many places I moved it. So 1, 2, 3, 4, 5. And I moved it to the right, or it was originally less than 1, so it's a negative exponent. So if I write it into scientific notation, now it's crystal clear that the only 2 significant numbers are here in this coefficient piece, the 1 and the 2. So all the other zeros kind of fall out or disappear, and we see that there's only 2 sig figs. And the last one is zeros at the end of a number without a decimal are tricky. And I will stay away from these, but a number would be something like this, 500. Okay. Did I put those 2 zeros there because they belong there? Did I put those 2 zeros there as placeholders? You don't know. You have to know a little bit more about the instrument. If you do need to report a number like this, the best way to do it is to write it into scientific notation. So if I wrote this number as 5.00 times 10 to the second, then it's crystal clear that all 3 of those numbers are important. There's 3 sig figs. So scientific notation, again, can help us out and really being clear about how many sig figs are there. The last thing I'm going to talk about in this particular video is calculations, sig figs and calculations. So unfortunately in the sciences, we don't simply record a number and stop. We typically math with those numbers. We're going to talk about 2 different categories. We're going to talk about multiplication, division, and we're going to talk about addition, subtraction, and they have 2 different sets of rules. So the first rule we see here is multiplication, division. In multiplication, division, we use what I like to call the weakest link. So we're going to look at all the measurements that were taken, and we're going to find the instrument that was the weakest or the least accurate, the one that gave us the least number of sig figs. That's going to be the instrument that limits us from writing more digits down. So if we look at these 3 measurements that were taken, so 5.02, 3 sig figs in that measurement. We look at this measurement, 89.665, 5 sig figs in that measurement. And we see this measurement, 0.10, 2 sig figs in that measurement. So this last instrument, whatever it was that took this reading, was the weakest link. So he's going to limit how many sig figs in our answer. So when I write my answer down, I'm limited to only 2 significant figures. Your calculators are not as smart as you would like them to be. So you're going to throw these 3 numbers into your calculator, and it's going to spit out this ridiculously long number. It doesn't take into consideration significant figures, so we have to do that for it. So this is the number that my calculator spits out. But knowing that this was the weakest link, I can only report 2 sig figs in my answer. So I would simply report 45 as my answer. Rounding is going to be the next questions. That's always the next thing that comes up. I'm not going to split hairs over rounding. General rule of thumb, greater than 5, round up to the next digit. If it's equal to 5, look at the next digit next to it. If it's less than 5, just leave it alone like we did in this one. We don't even change that number. So again, I'm not going to split hairs over rounding. I'll have a variety of answers that I would accept based on rounding rules. That's not something I'm going to get real harsh about. Right, so here's another example. Why don't you guys go ahead and pause the video and see if you can decide what it is that we would report. So using the weakest link, I see that the first number has 4 significant figures. The second number has 3 significant figures. The blue number is the number that my calculator spit out. I'm limited by our weakest link. I'm limited to 3 sig figs. So I report 0.966. If you reported 0.965, that's fine. What I'm looking for here is that you reported 3 sig figs. Okay, so draw a line in the sand, and we're going to go over to addition, subtraction. So completely different set of rules here. For addition and subtraction, we're going to be counting decimal places. The best way to do this until you get proficient at it is exactly how I set it up here. So go ahead and write out your addition subtraction problems. You're going to write the numbers stacked on top of each other. You're going to line up the decimal places. When doing addition subtraction, you're also going to be limited by the weakest link. But this time, to find the weakest link, we're going to count decimal places. So this first number is 4.8. It has 1 decimal place. The second number is 3.965. It has 3 decimal places. So 1 decimal place, 3 decimal places. When I report my answer, I can only report 1. So again, here's the number that your not so smart calculator spits out. Okay. And when I record my number, I only record 1 decimal place. Why is it helpful to stack these numbers on top of each other? Well, what you can do is you can identify the weakest link. You can identify the one that has the least number of decimal places, and you can draw a line there. So when you get to your answer, you know that you're going to keep everything on the left. You're going to throw away everything on the right. So that's why we just kept the 0.8. Here's another example. Go ahead and pause the video and see if you can work it out. So the weakest link in this example has 2 decimal places, this number here on the bottom. So if I were to draw my line, I would draw it after that 8. And then as I follow that down into my answer, I keep everything on the left, throw away everything on the right. So again, we have negative 8.66. In problems, and we'll see this in the next video when we get to density, in problems we may have to do a combination of different calculations. So what you would do is you would use your PEMDAS rules. When's the last time you saw PEMDAS? And the important part here is you're going to use the appropriate sig figs along the way. So if I do something in parentheses, I would pause, figure out the sig figs. Then I add and subtract, I pause, I figure out the sig figs. So you just want to use those rules along the way as you work through a problem. And if you need practice with that, here is an example for you to try on your own. Go ahead and pause the video, try this example on your own. Now that you've tried the example on your own, I'm going to click through the slide slowly so that you can see their answer. Okay. That's it for this video. So this is where I'm going to stop here. The next video we're going to dive into is also from Chapter E. We're going to talk a little bit more about density, which will be on your first lab. Hope you guys found this helpful.